So it's another good day because our keywords fit in our title. Today we're going to discuss quotient theorem and some theorems about trig derivatives and integrals. Alright, so let's get started here. So recall yesterday, or the other day, whatever day it was, we came up with this function that v of t equals n of t times p of t. So this was sort of our motivation for understanding the product rule. V of t was the total value of a fund, n of t is the number of shares, and p of t was the price per share. So when you multiply the number of shares times the price per share, you get the total value. And what we could do, actually, is we can solve this equation for n of t and get that the number of shares is equal to the total value divided by the price per share. And so the question is, well, what does that mean about the derivative of nt? How do we take the derivative of a quotient over here instead? Well, by using the product rule on our original equation here, what we can see is that we have a formula, an equation here, that involves the n prime of t term. And also another thing that we can do is we can replace this n of t with this equation here. And this will be useful in a second. So this means we have an equation here that only involves n prime of t's and other derivatives. So what we want to do is we want to solve for n prime of t. And I'm going to skip a lot of the algebra here. So if we solve for n prime of t, what we see is that we're going to get n prime of t in terms of the other functions. So the key is this formula down here, that we started with a function n, which we knew to be a quotient. We computed its derivative, and we get this mess of things here. Now it's an ugly formula to look at, but that's okay. So here we have the quotient theorem a bit more abstractly, and it says that the quotient of two differentiable functions f and g is going to be differentiable as long as you're not dividing by 0. And in fact, we have a nice little formula here for how to compute this thing, okay? So as long as you can memorize this formula, you're going to get it figured out. This formula is a pain to memorize, so the technical way to memorize is the lower function times the derivative of the higher function minus the higher function times the derivative of the lower function all over the lower function squared. Whew, that's a lot of work. So instead, what students often use, and what I do myself in my head when I'm computing these things, is I say low d high. So the low d high part is this part right here where we take the function g, our low function, multiplied by the derivative, the d of our high function. And next what we need to do is we minus high d low. So here we are subtracting f, the high function, d, the low function, times the derivative of the low function. And finally, the last part says square the bottom, and away you go. So we square the bottom function, and we're good to go. Alright, let's try it. So let's try to find the derivative of p of t equals t squared minus 1. So the first thing that's useful when we begin with these is we want to write these functions in terms of our high function, which is t squared minus 1. So that means f of t will be t squared minus 1 from our theorem, divided by our low function, 3t, so g of t is equal to 3t. And the reason we want to do this is because now we can compute our derivatives over here to save ourselves some trouble later. So the derivative of f will be 2t, and the derivative of g is 3. And now it's a matter of putting things in the right place, because we have that the derivative of this function that's a quotient is going to be now, according to our theorem, g times the derivative of f minus f times the derivative of g all over our original function g squared. And so here what we have is we have 3t times the derivative, which was 2t, minus the original f function, t squared minus 1, lots of parentheses going on here, times the derivative of g, which is 3, all over our original g function, 3t squared. So what we do is we really have this here. We have the low d times the derivative of high minus high derivative of low, square the bottom, and away we go. Now those gluttons of pain can go through and try to simplify this algebraically. I personally really like looking like this. If all you have to do is compute the derivative, leave it alone, okay? Just leave it. Don't simplify this down as simple as it gets. There's no reason to unless you actually need to plug numbers in later. And of course I meant substitute numbers. We don't plug numbers in. But just leave this alone. No need to simplify. Just leave it, please. So the next function we want to try taking the derivative of is tangent of t. Now, maybe part of you saying, that doesn't look like much of a quotient there. What are we really dividing? But then, you remember, and your high school trig teacher is really happy because you remember that tangent of t is really sine of t all over cosine of t. And we can take the derivatives of those. So again, using our quotient theorem, what we can do is we can say, well, our top function is going to be sine of t, and we can compute the derivative of this. We knew that this was cosine of t. We can also write our lower function, g of t, as cosine of t, and compute the derivative pretty easily as negative sine of t. That negative is super important. And now we can go ahead and compute the derivative. So this means that the derivative of tangent, according to our quotient theorem, well, we just got to follow along. So let's see. We have low function times the derivative of the high function minus high function times the derivative of our low function. Going to throw some extra parentheses in there just for fun. Square the bottom. And away we go. Now I know I just said we don't need to simplify this, but you're going to take the derivative of tangent enough, it's worth simplifying this a little bit. Okay, so let's simplify this. So this means we're going to get cosine squared t plus sine squared t in the numerator all over cosine of t squared in the denominator. Well, remember our one trig identity that matters. Our numerator is 1. Our denominator is still cosine of t squared. So we end up with secant squared t. So this is the shortened version that if you just want to memorize the derivative of tangent is really useful, because you probably don't want to do this every single time you need to take the derivative of tangent. So the key to remember here is the derivative of tangent is secant squared. Well, look at that. It's so important, we're going to put it into a nice box. The derivatives of trig functions. So, things you want to memorize. The derivative of tangent is secant squared. The derivative of cotangent is negative cosecant squared. The derivative of secant is secant tangent. The derivative of cosecant is negative cosecant cotangent. Ways to memorize this? Memorize. Cotangent goes with cosecant. I know it's kind of similar, but the cotangent's the other one. Cosecant's derivative has a lot of c's in it. Secant doesn't. You just got to memorize them. There's no shortcuts. We can also, using these, of course, take integrals of trig functions. Since we had up here that the derivative of tangent gives us secant squared, this means, of course, that the integral of secant squared is tangent x plus c. So integrals and trig derivatives are almost inverses. We just got to remember to plus c. So these are just the opposite rules we see above because they're integrals. So let's go ahead and practice taking some derivatives here. So this one, again, we're at the point where I'm going to do this a little bit faster here. So the derivative of x over x minus 1, which is of course just h prime of x. And if we go faster, this one is going to be low d high minus high d low, square the bottom, and away you go. Now, I personally am sorry, I just can't resist. I need to simplify it. The simplification here isn't bad. It's negative 1 over x minus 1 squared. So not so bad. I mean, the hardest part's really the setup and memorizing, but then it's a matter of just substituting and computing our way through. So here's another example. I suggest you pause the video for a few seconds and try this one on your own, and then we'll compare answers. I'm serious, pause the video. Okay, whether or not you pause the video, we're going to try it. So hopefully you didn't jump in and do the quotient rule here, okay? One of the problems students face whenever they learn a new rule or new theorem is that they just try to use it a lot, and I don't want you to do that. What I want you to do is I always want you to remember to rewrite first, okay? Rewriting can save you a lot of time and effort. So the first thing is, if we look at this, well, this is going to be equal to 5 times x squared all over 2x minus 10x over 2x. Okay? So when we look at this function here, it's really nice because this is going to simplify. This simplifies down to 5 halves in x minus 5, as long as x is not equal to 0. This is a function which has a very easy derivative. Q prime of x is simply going to be 5 halves as long as x is not equal to 0. Okay, this was a function that was just hiding and trying to fool you, making you think you needed to do the quotient rule when you really didn't. Okay, always try to rewrite first. So let's do one last example before we leave the quotient rule behind. So I suggest you take a minute, try to do this one on your own again, and we will meet back here and discuss it. So really pause the video this time and try it. There's nothing I can actually make you do to pause the video, so I guess we'll just go for it. Okay, so your first instinct might be to think, alright, I gotta do the quotient rule here. So let's try the quotient rule out. H prime of x means, let's see, let's set up our bar here. This is going to probably take a bit of work. So let's see, we need to take low times the derivative of the high function is negative sine of x, whoops, but it's positive because there's already a negative in there, minus the high function here, 1 minus cosine of x, times the derivative of my low function, the derivative of sine is cosine. Okay, and then finally I simply square the bottom, and away we go. So this is the answer. It's fine. It's not simplified at all, but again I've said you don't have to simplify this thing. It's okay. Now the problem with this is that trig functions like to be simplified and like to change what they look like a lot. Now the issue is, if you don't simplify, you may look it up in the back of the book, and the book says that the answer should be negative cosecant of x times cotangent of x plus the cosecant squared of x. What just happened there, okay? This is making you a little upset because you thought you'd done it right. Well, another thing that could have happened with this function is they may have rewritten it right away. We can rewrite 1 minus cosine of x over sine of x as 1 over sine of x minus cosine of x over sine of x. And if you remember your trig identities, this first one is, of course, cosecant of x minus the cotangent of x. Now, we just looked that we do have some trig formulas that help us take derivatives of these functions right away. And the way you do this is by using our quotient theorem. So if we look here, 1 over sine of x, I can take the quotient theorem and apply it to that. I can also apply the quotient theorem to this, but I can also just look it up in the table and see that h prime of x is going to be the derivative of cosecant of x, which is negative cosecant of x times cotangent of x, minus the derivative of cotangent of x, which is apparently negative cosecant squared of x. And after just a little bit of simplifying here, this is the answer the book got. So this is always the problem with trig functions, is that, as it turns out, this thing you found up here and this thing down here are definitely equal to each other. They are. You just have to work through a little bit of trig identities and you'll get that they're equal. The problem is that the back of the book doesn't know the answer you expect. Now, thankfully, WebWork is pretty good at this. If you put in an answer, it'll try like really hard to see if you've got the right answer or not. But for the back of the book, you may have to do some work on your own. This is also why I don't want you to simplify, because we simplify differently even though they're the same. Well, that's it for the video. As always, check the problems you're supposed to do online, post a question, try the quiz, and bring any questions you have to class tomorrow. Thanks.